Okay, so we just talked about the limit states for tension. We have yielding and rupture. Eventually we'll talk about shear, but there are similarly shear yielding and shear rupture. If we have both of them happen at a connection, it is called block shear. I personally think block shear, I don't know, maybe I'm just a visual person. I think it's kind of cool to visualize. So I've got some pictures coming up. And I don't know, I always found it kind of fun to calculate because it's kind of like a little geometry problem. Right, so let's say block shear is what you call it when a block of steel essentially tears out at a connection. It has at least two failure planes. Whereas before, when you're talking about tensile rupture, the entire cross-section ruptures or fractures. Now we're talking about only a portion of the cross-section. And it's going to have failure planes, at least one in tension and one in shear. And those failure planes are defined by the center line of bolt holes, and or the edges of your of a weld. So let's look at a couple of pictures to see what I'm talking about. All right, let's say you have, here we have a plate with, right, let's say this plate was on top of here, right? Actually it's not, but, right, if your plate is bolted onto something and you apply a tensile load and a portion of the plate tears out. Maybe the flange of an I-beam tears out. This little block tears out. Here's another one. See, we have a load, right, a tensile load, and this little section in the middle tears out. Here's an actual visualization from a test at Georgia Tech. That's what my block looks like, my block shear. You can see we have shear happening along this plane, shear happening along this plane, this plane, this plane, this plane, this plane. That's my shear rupture. And we have tension, right, perpendicular to the load on this plane, that plane, and that plane. So those are my failure planes. Right, at least one shear and at least one tension. Generally, as you can see, it's more likely to have two shears and one tension than two tensions and one shear. I don't know what that would be. Right? So that's some visualization. So let's look at if we have an angle. This is looking at it in plan. So this is my leg that's sticking up. If we have an angle bolted to a plate and we apply a load, let's look at a potential failure mode, right? Or limit state. Block shear in your angle. It means if I pull the angle, it'll shear along that bolt line, and it could have a tension, a potential rupture along that plane. As opposed to, if you look at pure tensile rupture, right, which would happen along that cross section, that entire effective cross section. Right? So the angle, right, leaves this little chunk behind. Those two used to be connected, and those two used to be connected. This is my shear plane and my tension plane. Right? Shear is parallel to my tensile load. Tension is perpendicular. Now, instead of looking at what if the angle, right? What if instead of leaving behind a chunk of the angle took a chunk of the plate below with it? We still have, now our shear plane is there, and our tensile plane is there. Right, there's my shear. And my tension. Now you noticed before, right, if I looked at the angle, right? Oopsies. If I looked at the angle, your shear, the area and shear might be different if you have block shear of the angle versus block shear of the plate. Right? This distance, right here, the shear might be longer or shorter than this distance, plus you have to multiply it by the thickness. And then similarly, my tension, Right, this looks like it might be a little bit shorter than this, but if my plate is thinner, it might fail more. You gotta check both. But that's how you could have block shear of part of your angle or block shear of a plate that's bolted to the angle. Another way to look at it, let's say we have a W shape bolted to a plate. Now what's not going to happen is you're not going to rupture the entire I-beam cross section, right? You're not, that's a really big cross section to break. That thing's going to yield. Right? But you could lose some of your flanges, right? If we're looking at the flanges, I'm going to break them off. This is my shear plane, right? Shear. And this would be my tension. Tension. And then if there's a plate on the other side, you'd have similar like that on the bottom. Right, that's my shear. And that's my tension. This is the flanges having block shear. Gosh, I can't spell tension. That's embarrassing. Tension. Now, what if the plate, right, that's what it looks like, right, what we just drew. If blocks of the, alright, there's my, I'm just looking at it in plan and in isometric, right? That's what it would look like if you had block shear of the flanges. They leave a chunk behind while that tensile load is applied. Right, from there to there. Now what if I look at the plate itself? I want you to look at it and think about, are there multiple ways for this to have block shear? Because the answer is yes. If it's just looking at an actual plate, it could fail. Chunks could break off similar to right, two little chunks could break off, but what would be more likely, right, is if one middle chunk broke off, right? This length is probably shorter than these two put together. You never know. this has 2 tensile planes. This only has 1. What would that look like? We'll look at it on the next slide, right? If 2 little chunks broke off, oops, versus 1 chunk. All right. In actuality, there could be, right, there's my tension. There could be a third one where, like, that chunk broke off. But that's why I think it's kind of fun to get to look at, you know, these 2 could chunk off the middle, or right, like something like that could break off too. This is of the plate. So those are some examples of block shear with a bolted connection. A block shear can also happen if there's a weld. If we're looking at an angle welded, what's less likely to happen, obviously, if it was to rupture, right, it would just rupture through the entire cross section of the angle. So, but it could block shear a chunk of the plate. Right? If we're pulling it, we've got our shear and our tension. Right? Like that. Yeah, there's 2 different, there's 2 different ways this could happen, actually. Right? You're not going to have block shear in the, I'm air quoting, block shear in the angle, because that would actually just be rupture of the angle. But you could have block shear in the plate. There's 2 different potential methods. One is if this little portion, right, this little rectangle block shears, or if actually just this whole that whole rectangle, this whole corner kind of pops off. Oh, I chose poorly. I was backwards. Right. No, I just erased that. Should actually look at my notes what I'm doing. Right. So you could have the rectangle, right, this whole section, or the corner, block shear off, like that. Right, so again, this is my tension plane. Right, because if you think about it, that's a lot less material to break, right? This top one is a lot less material to fail than the bottom one where you have the two shear planes. And the tension, yes, the tension plane's a little bit bigger in the top one, but maybe not compared to how much effort it's going to take to rupture those two shear planes. But it's always good to calculate both. So that is some visualizations of block shear. So now we've talked about all the different limit states for tension members. Gross member, we have the yielding, we have the rupture over the effective area, and then block shear, which can occur if you have a connection in tension.